So this is experiment number 2, at least in 2019, the manual says it's number 2. You start with acetyl glycine, reacting with benzaldehyde. You have some sodium acetate and some anhydride, acetic anhydride, to make this condensation product. So that's our product today. It's yellow. Everything else before it had no color. And I'm just going to quickly show the TLC. A couple of times I've run it 2 different ways. This one was run in 1:1 pet ether. This one was 3:1. And you can't really see it, but basically what happens is in both cases there's leftover benzaldehyde. This is a nicer one, they're in straight lines. So there's leftover benzaldehyde. And the product, which is yellowish, you can see with your eye, will stick to the gel. So a couple things I want to make a comment about this is, this original procedure was taken from Organic Synthesis, which is an industrial journal. And in this case, they're basically saying, yeah, that's a benzaldehyde. You react it with your acetyl glycine, sodium acetate, and it makes that. So this is the industrial process, and it even tells you a little bit. The second step they do is they treat it with water later to open up the ring. But this is what we're looking at making. So if you read through this, you might see a little bit about the recrystallization process and what to be. But as far as the names yeah, the names, they're going to call it, this is the name of the final product here. This item, they call it the azelactone of benzaldehyde. So in any event, that's a procedure from, I'm reading this at the same time, yeah, Organic Synthesis. What's interesting is Professor Jim Green suggested, keyword, possibility for a possible mechanism. It's not expected at all that you have a mechanism for this one, but what you're going to see as you follow where he's going with this, right? It's got a number of steps. There's an aldol in there at some point. And the dollar, that's the money sign, maybe a little expensive to do this. Aldol, and it goes this way. So you can see why you're not expected to do this. It's a very complicated, suggested mechanism. Second route, as before to get to here, takes you to that. Just in case anybody's interested, these are 2 suggested mechanisms that he suggested. You don't have to do that. I think we're good. So now I'm just going to go right to the spectra. So first things first. This is benzaldehyde, and you notice whoever ran it this year, it was Joel Zlotnick that ran it. You get nice sharp peaks. It's a decent quality IR, but most importantly, see these 2 numbers right here? See those 2 peaks? That's the classic Fermi doublet of that hydrogen of an aldehyde, the CH particular stretch. Fermi doublet right there. This would be the CH stretch of aromatic carbons with H's stretching. This peak is obviously the carbonyl C double bond O stretch. Whenever you have an aromatic ring, normally you always have some stretches right around the 1600 mark, and even there's a little bit of space and you see another one. So normally a lot of books like Pavia will circle these 2 and call it C double bond C aromatic stretch. Not 100% sure what 1203 is, so I'm not going to circle that one. The only thing I'm going to look for is mono-substituted. When you look in Pavia, they'll tell you that there's 2 particular stretches, if you see them, high 600s up to 752. So I would circle these 2 and call it CH out of plane bending, so CHOOP bending of a mono substituted aromatic ring. So that's it for that one. Then we move on to acetic anhydride. Unless I'm delusional. No, it is in this one. I don't want to get it confused with number one. So, what's interesting is our acetic anhydride always has these two little bumps. One of them, 2942, is supposed to be the CH methyl group stretch. This one, 3025, arguably is a contaminant of something, because normally above 3000, it's a sp2 hybridized carbon. So I would ignore the 3025. This is the anhydride, two carbonyls with the O in the middle. It's the C double bond O stretch that's coupled through these bonds to give you this two-peak, very broad thing right there. Other than that, you could arguably say, see this big characteristic thick band, you could arguably call that the C single bond O stretch of some sort. And that's about all I would worry for that. Acetylglycine, we talked about this the other day, and let's just see if on the spot how I would babble about this one. It looks to me like somebody's done a little bit too much background correcting in this region, because the acetylglycine, which I think I just broke one of the biggest rules, anytime you hand in a spectra, it is horrible if you do not put in the structure. You have to put it in. Acetylglycine. So this is just another example. You could reprint your own from before and do it again. So this is the NH stretch. Normally this whole region, somebody corrected that one and drew it down, but normally this ugly region, you could just circle kind of like so and say it is the OH carboxylic acid stretch, which is very broad. Then in this region, the 1720, see how sharp that carbonyl is? It has to be attributed not to the amide, but to that carbonyl stretch. These two, you could circle both and say it's I don't know which specific one is which. One of them is related to the amide C double bond O stretch. The other one is related most likely to the NH bend. That one turns out to be quite broad. Other than that, I really wouldn't circle anything else that I'm sure of. The product. This is kind of an interesting beast. So remember how I said you stare at this and you say to yourself, I'm not even looking at the spectra at the moment, what kind of functionality do I have? I gotta find my blip. Oh, here we go. We have an aromatic ring, so we know the characteristic IR stuff for that. We have another C double bond C bond. We have an ester, but it's in a ring, arguably, but we have a carbonyl. Normal esters are 1740. We'll see where this one ends up. Complicating this, maybe, is a C double bond N, and it's in a 5-membered ring. So long story short, I'm thinking to myself, I'm not even sure exactly what I expect to find for this. So I'm gonna have a look and see what does make sense. And this big absorption here, man, that looks like water. So normally what you're going to find in water, on top of the IR, we have a thing of water. You see a big peak like this, and then down at like 1650-ish, but see this, the sketchiness right here? Someone buried right in here. I would say this definitely looks like moisture. There's nothing in here that would indicate that. You may or may not have this peak in yours. Everybody's going to be different when it comes to water. But these peaks right here, these ones above 3000 are sp2 hybridized carbons with hydrogen stretching. The little blips here, the 29 that's just below, that would be your methyl group. See those hydrogens on that carbon stretching? So I could label that one. What do we got here? Well, 1776. Remember how I said the normal ester is 1740, but inside of a 5-membered ring, one of the double bonds in it like this is going to be more strained and tight. So that carbonyl absorption should be 1776. 1655, very pronounced. Not likely to be the carbon-carbon double bond stretches of the ring. It's possible, likely, I would say it's this one, the carbon-carbon double bond stretch of that one external to a ring. Very likely that's what the 1655 is. And then your aromatic ring has the characteristic, remember, right at 1600, a couple of peaks, and then the next lowest 1490. So that one and these two right here are the aromatic ring carbon-carbon stretching. What we might look for, but see, you know, am I going to say that this one here is the C carbon-oxygen single bond stretch? I'm not 100% sure. So I really don't bother labeling because I'm not sure. Mono-substituted ring, high 600s and up to 750. So, I mean, we could circle these two, say mono-substituted OOP bend. So that's IR. You'll notice I do not have acetic anhydride UV scan. You guys should. So you include it, you put the structure in. This is the one you already seen in my previous video. It's the absorption related to pi to pi star is what that one is, and it's normal. Run in ethanol, it's this. If you ran in water, it might be slightly different. Your product should look kind of like this, right? And what's interesting is this is your characteristic absorption for it. It's yellow. So somebody could say at first glance, see here's 400. I ran it concentrated enough that you can see that there's a shoulder right there. Imagine if we concentrated this much higher. This right here would turn into something looking like this. So it tails into the visible. Talk about that in discussion. But the UV looks simply just like that. Now we go over to the NMR. I don't have a C13 on me handy. I don't know if I posted it online or not, but this is a typical. So there is the TMS at 0. This is your methyl. You know that methyl that I've labeled E right here? That one. There's one hydrogen coming off at D right there. And it turns out the pattern in the aromatic region, and see that tiny little stick right there? That is chloroform D. So if your compound was really dilute, that chloroform D signature of the solvent, NMR solvent, would be higher. This was concentrated enough it looks tiny so we can ignore it, but others it's taller. But the three peaks areas is this one, and this one is your product. This one right here, which integrates to 1, it's going to be that hydrogen right there. And then normally what happens is the ortho position of this stick closest to some sort of pi bond, position A is normally drawn out to the left. So if this integrates to 2, which it does, you circle this and call that position A. By symmetry, these two ortho ones are the same. B and then C is overlapped and in this peak, which integrates to 3. That's your proton. And now we just rumble over to Discussionville. So I'm going to go quickly through it just to give you some ideas of what you should start talking about. This is just a very quick few ideas to start you on a discussion. There's always more if you want it. So let's talk about color. The starting material has no color. The product is yellow. So in the world of molecular orbital theory and what we were talking in class, your starting materials, the pi to pi star transition, this gap is big enough, right, that it's not in the visible range. This is the UV range, and we already seen that. Your product, though, when you're done, conjugation makes the pi to pi star gap shrink and get closer to the visible range, which is what I drew a diagram here. The UV that I showed you, if we were to run it much more concentrated, it would max out, but then the tailing effect would show absorption just above 400. So in other words, you could talk about how if this compound is absorbing the purplish, you're going to see what's left over, which to our eyes appears yellow. The same idea is going to happen to your experiment number 3, which is a yellow product. Same similar thing. When you run your normal UV, it looks like it's flat here. Crank up the concentration of it, you're not going to get the nice curvature up here, but you'll see how it tails off and absorbs a little bit of visible region. So that takes care of that color. And then the browning in the class and heat. So one of the things about your discussions is you are absolutely encouraged to walk around and look at how other things are going. And anybody doing experiment 2, you're going to see that many others, some is just bright yellow all the way through, others is turning dark brown. So the point is, dark brown, when you know it's yellow product, when you see that, that's a sign of organic decomposition, where organic molecules are falling apart to an extent. So some of the folks, and then you say, what if they're heating it too much, right? Is that a problem? But if everybody's heating it in a heat bath the same way you did, then you start to wonder. But a lot of organic reactions, sometimes, maybe it's the tiniest thing in your glassware or whatever, but all permutations that people run in the experiment are not going to be identical in the color difference. Some people have decomposition. And even stranger is the yield. Everybody in the room have different. Some people have a lot of yellow crystals. Others have a tiny amount. Others are having something that's not crystallizing at all. So even though it looks like we're running the reaction the same way, and this is a valid discussion point that in industry, if you do multiple trials and you find such variability with the amount of solid you're getting, you want to work on what is affecting that. So if we wanted to investigate that variability of yields further, then what we could do is set up multiple trials where we carefully have pristinely clean glassware. How we make each trial is identical. We make sure the heating process is done in even the same water bath if you want. And we can monitor the reactions by HPLC. So you take tiny aliquots of the reaction as it proceeds through the hour or whatever, and you monitor your starting material diminishing and the product forming. That is one way of testing the variability. And so that's almost like an industrial process of if you were doing this on a 10 kilogram basis and you wanted to find out why sometimes it runs good, sometimes it doesn't. That's the type of thing you could do. That could be mentioned if you want. Yield. You also have to run the filtrate. Anytime you filter, keep crystals, to find out where all the organic material went, all that starting material you're using, the benzaldehyde, the acetyl glycine starting material, and the, what was the other one? Acetic anhydride. Where did it all go? So HPLC is the best way to monitor your filtrate. The TLC, as we find, everybody's TLC, because you're taking a TLC on your crude, it shows leftover benzaldehyde right away. So obviously, you have to go back and make a comment on your limiting reagent. I don't know, was benzaldehyde in excess? Was it your acetyl glycine that was limiting? Because the TLC is showing that there's leftover benzaldehyde coating your yellow crystals. So that's something you could talk about too, a little bit about yield. A reaction energy diagram. The one thing that I did not talk about here, but when this reaction, this is energy, and then this is as the reaction proceeds. Since we don't know the official mechanism, we can't, all we know is this: the starting material is your acetyl glycine, right? So that being said, the product looks like this. So just for qualitative purposes, if all you're doing is matching the energy of your starting material versus your product, I'd say the product definitely, with all those multiple bonds and everything else, multiple functional groups, right? Its line, when the reaction's done, as far as just that one organic compared to this one, should be higher in energy. Remember, this does not mean the overall reaction, because let's face it, acetic anhydride is up here, right? Sodium acetate, benzaldehyde would be higher. Benzaldehyde might be here. Plus then you heat it. So whatever the height of all these peaks and hills are, whatever that is, we end up here for the organic of interest product. All the other side products would be all over. How could you tell if the overall reaction itself was literally exothermic or endothermic? And the way you could do that is you could run this reaction, right, at room temperature, and if it's inside a calorimeter and it starts generating heat by giving it off, the temperature will go up. If as the reaction proceeds, it starts taking energy in, then you could find out that way. For instance, that's one. But there's no obvious signs that this reaction was exothermic. We had to heat it as well. So that's kind of an assumption. We say the overall reaction is probably endothermic, and it makes sense because a lot is going on and you have to make a very reactive final product as well. So it makes sense it's likely to be an endothermic reaction. So I think that rounds out this one.